Hello, everyone, and welcome to another episode of Chemistry. Today's lesson is about chemical bonding. In one of the previous chapters, you learned two different types of chemical bonds: ionic bond and covalent bond. Atoms bond ionically to form ionic compounds, while others bond covalently to form molecular compounds, or simply molecules. So, how do atoms bond together to form molecules? There are many different bonding theories out there that explain how molecules are formed. Some can explain things better and more accurately than others. But their main purpose is the same: to predict how atoms bond and to explain the stability and reactivity of molecules. The Lewis theory is the simplest bonding theory, or model that explains how molecules are formed from atoms. In this theory, Lewis structures are drawn to illustrate molecules. The Lewis theory uses Lewis symbols, where the symbol of the element is surrounded by dots, which represent the number of valence electrons for that specific element. Using a periodic table, one can easily determine the number of valence electrons. The number of valence electrons matches the group number of that element. For example, group 1A elements will have 1 valence electron, and group 8A elements will have 8 valence electrons. Shown here is the Lewis symbol of sodium, with 1 valence electron represented by a single dot. Here's calcium with 2 valence electrons, boron with 3, and here's a few more examples of Lewis dot symbols. You've also learned in the past that atoms with 8 valence electrons are stable because they are said to have a complete octet. They follow the octet rule. All of the noble gases are considered stable. They all have a complete octet except for helium, which has a duet, meaning 2 valence electrons. As you can see here, helium has its first energy level completely filled, which makes the atom stable. Lewis dot structures can be used to show how atoms bond covalently to form molecules. In one of the previous chapters, you learned how to draw the Lewis structures for diatomic molecules such as fluorine gas, oxygen gas, and nitrogen gas. The first step is to draw the Lewis symbols for each atom in the molecule, as shown. Notice that each fluorine atom lacks an electron to complete its octet. By sharing 2 electrons, both fluorine atoms are now stabilized, forming a covalent bond. As you can see, both fluorine atoms now possess a total of 8 valence electrons. These 2 electrons that are being shared by the 2 fluorine atoms are called bonding electrons, also known as a bonding pair. All of the other electrons are called non-bonding pairs, or a lone pair. A bonding pair can also be represented by a line, a single line, connecting the 2 atoms. A single bonding pair is known as a single bond. Now let's draw the Lewis structure for oxygen gas. Again, the first step here is to draw the Lewis symbols for each oxygen atom. Then start sharing the electrons so that both oxygen atoms will have a complete octet. In this case, a total of 4 electrons will be shared, forming a double bond. Here's another example of a diatomic molecule. Last time you learned that the two nitrogen atoms in nitrogen gas share a total of 3 bonding pairs, known as a triple bond. You also learned that hydrogen gas is a special case, in such a way that it doesn't really follow the octet rule. Since hydrogen only contains 1 electron, the 2 hydrogen atoms in hydrogen gas can only form a single bond. In today's lesson, you'll learn how to draw Lewis structures for polyatomic molecules. There's a few different methods that you can use in drawing Lewis structures, and here's the first one. First, you need to count the total number of valence electrons of the molecule. If we have ammonia, for example, which has a chemical formula NH3, this molecule has a total of 8 valence electrons, 5 coming from the nitrogen and 1 for each hydrogen, a total of 8. Then divide this number by 2 in order to get the total number of electron pairs. In this case, 8 electrons divided by 2 gives us 4 electron pairs. The third step is to determine the central atom, and here's a few rules regarding determining the central atoms. Hydrogen is never a central atom, but carbon, on the other hand, is always the central atom. The following elements, such as nitrogen, oxygen, boron, all the way to iodine, can also be a central atom. And so, in our molecule, NH3, the nitrogen is our central atom. Once you've determined the central atom, the next step is to surround the central atom with 4 electron pairs in order to satisfy the octet rule. Remember that we have counted a total of 4 electron pairs for this molecule, and we have distributed all of them around the central atom. Then surround the central atom with the remaining atoms, as shown. So the hydrogens, because they're not the central atom, they are known as the terminal atoms. If there's any electrons left, distribute them equally among the rest of the terminal atoms surrounding the central atom. In this case, we don't have any more electrons left to distribute. But if necessary, start forming double bonds or triple bonds to make sure that each atom has a total of 8 electrons, except for hydrogen, of course. Let's look at a few examples here. We have carbon tetrafluoride, nitrogen tribromide, and carbon dioxide. Draw the Lewis dot structures for each molecule. Here are the summarized steps. First is to count the total number of valence electrons for each molecule. So for CF4, carbon tetrafluoride, we have a total of 32 valence electrons, 4 from carbon and 7 for each fluorine. Divide that by 2 and we get the total number of electron pairs, which in this case is 16. Carbon will be the central atom, and so we're going to surround the central atom with 4 electron pairs in order to satisfy the octet rule. Then we're going to surround the central atom with the terminal atoms, right? The remaining elements, which in this case, 4 fluorine atoms. The next step is to distribute the remaining electron pairs around the terminal atoms, and we have a total of 12 pairs to distribute. And then we have to make sure that each element or atom within the structure satisfied the octet rule, which in this case they all do. And so we don't have to double check for double or triple bonds because each atom in the structure already contains 8 electrons. Next one here is nitrogen tribromide. It has a total of 26 valence electrons, 5 from nitrogen and 7 for each bromine, a total of 26. We're going to divide that number by 2 in order to get the total number of electron pairs, which in this case we have 13. Nitrogen is the central atom, and so we're going to surround the central atom with 4 electron pairs. Then surround the nitrogen with the rest of the atoms and electrons. We have 9 electron pairs to distribute equally among the 3 bromine atoms. And the last one here is carbon dioxide. This molecule has a total of 16 valence electrons with 8 electron pairs. Carbon in this case is our central atom. We're going to surround the central atom with 4 electron pairs. And then we're going to just surround the central atom with the 2 remaining atoms. And we have 4 electron pairs left to distribute equally among the oxygen atoms. Since the oxygen atoms don't have a complete octet, they would have to form multiple bonds. Here you can see that the carbon atom has a full octet, but the oxygen atoms don't. The non-bonding pairs from the carbon will become bonding pairs shared with the oxygen atoms. Carbon must form a double bond with each oxygen atom. Here you can see that the carbon dioxide now shows double bonds. The carbon is double bonded to the oxygen on the right-hand side and also the oxygen on the left-hand side. So these are the Lewis dot structures for the 3 molecules. There's another method that you can use to draw Lewis structures, which some people actually prefer. Let's take a look at these 4 different molecules and draw their Lewis structures using method number 2. This method tells us that the central atom is the element with the least number of atoms in the molecule. So in ammonia, NH3, nitrogen would be the central. In carbon tetrafluoride, it would be carbon. And in carbon disulfide, it would also be carbon. And finally, the 4th one here is C2H4. Carbon is also the central atom. So the first step here is to draw the Lewis symbol of the central atom, in which case nitrogen. Then draw the Lewis symbols of the remaining atoms around the central atom. And the third step here is to connect the dots between the central atom and the terminal atoms. And finally, check that the octet rule is satisfied for each element. Form double bond or triple bonds whenever possible. Here you can see that nitrogen has 8 valence electrons, which basically satisfies the octet rule. Hydrogen, on the other hand, doesn't require an octet in order to be stable. All right, in CF4, carbon tetrafluoride, first draw the Lewis symbol of the central atom, which is carbon, then surround the central atom with the Lewis symbols of the terminal atoms, the fluorines. And then connect the dots and any double bonds whenever possible. And here you can see that carbon has a total of 8 valence electrons, and each of the fluorine atoms also contain a total of 8 valence electrons. So they all follow the octet rule. So this is the Lewis dot structure for carbon tetrafluoride. Next one here is carbon disulfide. So carbon again is our central atom. So draw the Lewis symbol for carbon and then surround it with the terminal atoms, sulfur, and then start connecting the dots. So once you've connected the dots, you can see that carbon here only has a total of 6 electrons, right? And you look at the sulfurs, they only have a total of 7. And so the sulfur still lacks one other electron to satisfy the octet rule, and carbon needs 2 more in order to satisfy the octet rule. And so what we're going to do is we're going to form another bond, a double bond. So what I did here is I just moved that single electron up top above carbon and pair it with the one at the bottom. And then I connected the dots here to form double bonds. So this is a cleaner version here down at the bottom. So this is the structure, the Lewis dot structure for carbon disulfide. And if you notice, carbon disulfide has the same structure as carbon dioxide. All right, and the last one here is C2H4, and you can see that carbon is going to be the central atom. It is possible to have 2 central atoms, and so we're going to put them both as our central atom here. And then we're going to surround the 2 central atoms with the terminal atoms. So we're going to split it evenly, 2 on the left, 2 hydrogens on the left, and another 2 hydrogens on the right. And then we're going to start connecting the dots. So hydrogen is now stable because it has a duet, right? 2 electrons. And then we're going to do the same thing for carbon. We're going to connect the dots, but then when you count the total number of electrons for each carbon, they only have a total of 7. And so the unpaired electrons here will then form another bond. Okay, so we can rearrange that, connect the dots, and now we have a double bond formed between the 2 carbon atoms, the central atoms. All right, let's look at a few more examples here. You can pause this video if you want to try this out. All right, so we have 4 different molecules here. We have NCl3, CH2O, PF3, and CCl2F2. And we're going to use method number 2 here to draw the Lewis dot structures. So the first one is NCl3. All right, so the first step here is to determine which central atom we have. And here we have nitrogen. All right, so you're going to draw the Lewis symbol for the central atom. And here nitrogen has 5 dots because it has 5 valence electrons. And then we're going to surround the central atom with terminal atoms, the remaining atoms, chlorine. So we have 3 chlorines surrounding the central atom. And then we're going to start connecting the dots here. And once you've connected the dots, double check to make sure that each atom contains 8 valence electrons, right? They have to satisfy the octet rule. So looking at nitrogen, you can see that it has a total of 8 valence electrons. Chlorines, the 3 chlorine atoms here, same thing. And so all of these atoms satisfy the octet rule. So this is the Lewis dot structure for nitrogen trichloride. The next one here is CH2O. So carbon is always a central atom. Hydrogen is never a central atom. Oxygen can also be a central atom, but carbon basically trumps oxygen. All right, so we're going to put carbon as a central atom here. And this is the Lewis symbol for carbon. And then we're going to surround the central atom with the terminal atoms and start connecting the dots. So as you can see, the central atom, carbon, lacks another electron. And so it has to form another bond with an oxygen, because oxygen here also doesn't have a complete octet. And so they're going to have to form a double bond. And here's a cleaner version. This is the Lewis dot structure for CH2O. Third one here is PF3. So phosphorus is our central atom. And we're going to surround the central atom with the terminal atoms and start connecting the dots. And again, you want to double check and make sure that each atom satisfies the octet rule. And as you can see here, all the atoms contain 8 valence electrons. So this is the Lewis dot structure for phosphorus trifluoride. And last one here on the right, we have CCl2F2. Again, carbon is always the central atom. We're going to put that in the middle and then surround it with the remaining atoms. Connect the dots and recount and make sure that each atom has a complete octet, and they do have a complete octet. So this is the Lewis dot structure for dichlorofluorocarbon. All right, so I've mentioned earlier that hydrogen does not have to satisfy the octet rule in order to be considered stable. And so hydrogen is one of the exceptions to the octet rule. Some elements can have what they call an incomplete octet, which means they don't have to have a total of 8 electrons to be stable. Beryllium, boron, and hydrogen are all examples. In the Lewis structures for both boron trifluoride and boron trihydride, also known as borane, the central atom boron doesn't have to have a complete octet to be stable. As you can see here, the boron in both structures only have a total of 6 electrons, yet they are both stable molecules. Some elements in the periodic table, on the other hand, can have an expanded octet, meaning they can have more than 8 valence electrons as the central atom and still remain stable. Elements on the third row and below in the periodic table can have an expanded octet. In fact, they can have up to 12 electrons. Here are some examples of molecules in which the central atom has over 8 valence electrons surrounding it. Here, arsenic pentafluoride is a toxic gas. You can see in the structure that arsenic has a total of 5 single bonds, which equates to 10 bonding electrons. This is acceptable because arsenic is on the 4th row on the periodic table. Sulfur hexafluoride is a heavy gas. Sulfur is on the 3rd row of the periodic table, which means it can handle more than 8 electrons. Here it contains 6 single bonds, which equates to 12 bonding electrons. This last one here is the sulfate ion. You can see that its structure shows sulfur containing a total of 6 bonding pairs, or 12 bonding electrons. And these are the last two concepts that I wanted to cover in this chapter: resonance structure and formal charge. Some Lewis structures can be drawn in different ways and still be considered stable. These are called resonance structures. Many polyatomic ions, like the carbonate ion, have resonance structures. Following the methods in drawing Lewis structures, we get the following for the carbonate ion. You can see that you can have the double bond formed between the carbon and the oxygen on the right. However, the carbon can also form the double bond with the other oxygens as well. So these other two structures shown here of the carbonate ion are possible structures, and they are called resonance structures. The last concept is the formal charge. This is the charge an atom would have if all bonding electrons were equally shared between bonded atoms. And it can be calculated for any element in a Lewis dot structure using this formula shown here, which is equal to the number of valence electrons for that element minus the number of non-bonding electrons minus the number of bonding electron pairs. Let's look at some examples here and apply the concept of formal charge. Here are three different molecules containing the elements carbon and oxygen. Determine the formal charge for each oxygen. Here's the formula for the formal charge. Looking at the carbon dioxide, the oxygen on the left would have a normal charge of 0. Oxygen has 6 valence electrons, minus 4 non-bonding electrons, minus 2 bonding pairs, and that gives us 0 formal charge for this oxygen. The second oxygen on the right would have the same formal charge of 0. For the second structure here is the carbonate ion. This oxygen on the left has a formal charge of -1. 6 valence electrons for oxygen minus 6 non-bonding electrons minus 1 bonding pair equals -1. This second oxygen at the bottom is similar to the first one. And the last oxygen on the right has 0 formal charge. The structure on the right is carbon monoxide. The oxygen has a positive formal charge as shown. Oxygen has 6 valence electrons minus 2 non-bonding electrons minus 3 bonding electron pairs, which equates to +1. So this oxygen has a formal charge of +1. Here's a few things to consider when dealing with formal charge. When determining the formal charge, remember these rules. The sum of all formal charges in a neutral molecule must equal 0. So that means that when you add up all the formal charges of each of the element within a given molecule, they should add up to 0. The sum of all formal charges in an ion must equal the charge of the ion. Okay, so for example, if we have carbonate ion, which is CO3 with a -2 charge, when you add up the formal charges of all the elements in that ion, it should equal -2, which is the ionic charge of that polyatomic ion. All right, third one here, small or zero formal charges on individual atoms are better and more stable than large ones. And we'll see an example for that in a little bit. And the fourth one here, when formal charge can't be avoided, negative formal charge should be on the most electronegative atom. So since we didn't really talk about electronegativity here, you can ignore the last one. All right, so we can actually use the concept of formal charge in order to determine which structure is more stable. Because again, we can have resonance structures, right? Structures that are structures of the same molecule but different in the electronic arrangement. So here's an example. Based on formal charges, which Lewis structure do you think is more stable? So in order to solve this problem here, we have to determine the formal charges for each element in the structure. So here's the summarized way to determine formal charge. We're going to look at the number of valence electrons for each element, the number of non-bonding electrons around the element, and the number of bonding electron pairs for that element in order to calculate the formal charge. So for hydrogen, it has 1 valence electron, carbon has 4, nitrogen has 5. Okay, and then the number of bonding electrons, looking at the first one here, HCN, hydrogen has 0 non-bonding electrons, carbon has 0 non-bonding, nitrogen has 2. On the right-hand side, that hydrogen also has 0, that nitrogen has 0, and the carbon has 2. All right, and the number of bonding electron pairs, for hydrogen, it's got 1 bonding pair, carbon has a total of 4, nitrogen has 3 bonding pairs, and then on the right-hand side, we have 1 for hydrogen, 4 for nitrogen, and 3 for carbon. And now we can use the equation, the formula for formal charge. It's basically we're subtracting all these numbers. So 1 minus 0 minus 1 for hydrogen, that would give hydrogen a 0 formal charge. For carbon, it would also be 0 because we're subtracting 4 from 4, and then 0 for nitrogen as well. And then for the structure labeled B here, that would be 0, 1, and -1. And so because when you're looking at these factors written above, it says factor number 3 here, it says small or 0 formal charges on individual atoms are better and more stable than large ones. So in that case, structure A, this one right here, would be the more stable structure. It's more stable because the formal charge for each element within the molecule is minimized. All right, so let's look at a few more examples here and determine the formal charge on each element in the following polyatomic ions. Again, you can pause this video if you want to give them a shot. Looking at the 2 oxygens at the bottom here, looking at NO3. Okay, NO3. These 2 oxygens will have the same formal charge because of the fact that it has the same number of non-bonding electron pairs and the same number of bonds, right, bonding pairs. And so what we're going to do is we can determine the formal charge for each element in this molecule or polyatomic ion. All right, and here's the formula for formal charge. And we can label the oxygens here We have oxygen 1, oxygen 2, and oxygen 3, just so we know which one we're trying to look at. All right, so for the nitrogen, nitrogen has 5 valence electrons. So we're going to use this formula here at the bottom, right? Number of valence electrons minus number of non-bonding electrons minus number of bonding electron pairs. So for nitrogen, nitrogen has 5 valence electrons. And then looking at this nitrogen here, it's got 0 non-bonding electrons and 4 bonding pairs. So that means we're subtracting 5 minus 1, 5 minus 0 minus 4. So in that case, this nitrogen has a positive 1 charge, formal charge. All right, for oxygen 1, the first oxygen at the bottom here, oxygen has 6 valence electrons, and it has 6 non-bonding electrons and 1 bonding pair. So 6 minus 1 gives us negative 1. So that oxygen at the bottom, again, is the same as the oxygen on the right, and they both have a negative 1 formal charge. And finally, the oxygen up top, labeled 3, it's got 6 valence electrons minus 4 non-bonding electrons minus 2 bonding pairs, gives us 0. So the one up top has 0 bonding pair. 0 formal charge. All right, now let's look at the next structure here. Let's look at sulfur first. Sulfur is in group 6, so it's got 6 valence electrons minus 0 bonding or 0 non-bonding electrons minus 5 bonding pairs. Right, so that gives us positive 1. So that sulfur has a positive 1 formal charge. And notice that sulfur has more than 8 valence electrons because sulfur is on the 3rd row in the periodic table. All right, oxygen labeled 1 would have 0 charge because it's 6 minus 4 minus 2 gives us 0. The second oxygen on the right here would have a negative 1 charge. The one at the bottom would also have a negative 1. And same thing for the fourth oxygen, negative 1. All right, let's look at NH4. Nitrogen would have, so nitrogen has 5 valence electrons, minus 0 non-bonding, minus 4 bonding pairs. That would give it a positive 1 formal charge. And the hydrogens have 1 valence electron minus 1 bonding pair, gives it 0. All right. All right, now let's look at the structure on the right. Looking at the first carbon here, carbon has 4 valence electrons minus 0 non-bonding minus 4 bonding pairs, gives it a 0 formal charge. Second carbon here, same thing, right? It has 4 valence electrons minus 0 non-bonding minus 1, 2, 3, 4 bonding pairs, so that's 0 charge. First oxygen up top will have 0 formal charge. 6 valence electrons minus 4 non-bonding minus 2 bonding pairs equals 0. On the other hand, this oxygen on the right would have 1 negative charge. So 6 minus 1 gives it a negative 1 charge. All right, so that's how you determine the formal charge for each element in a given structure. And if you notice, these are the polyatomic ions: nitrate, sulfate, ammonium, and acetate. So, if you were ever wondering, that negative charge basically is the overall charge of this molecule, the net charge, right? Sulfate has a negative 2, because 3 of the oxygens have negative 1 charge and then 1 positive, so the net charge is negative 2. Same thing for ammonium and acetate here. Alright, and that's the end of chapter 9. Thank you for watching, and if you like this video, please subscribe, and I'll see you next time.